All right, so sound waves are longitudinal waves, which when we were initially discussing waves, we talked about that the fact that there are different types of waves, some that require molecules and some that do not. So again, we are discussing mechanical waves right now, which require a medium, which is just a word that means we have some sort of atoms, molecules, particles, matter. Okay, a lot of times we say it is the material that the wave is passing through. So sound is a longitudinal shape wave, and just to remind you, longitudinal waves have alternating phases of compression and rarefaction. So you can see in the image here that we definitely have areas of very dense air, or the particles here are packed in very tightly, and then immediately following that we have a space of very low density. We have very few particles in that particular space, and so this is going to represent our two phases, or the two parts of our wave cycle. So one complete wave must have both parts of the motion, or both phases of that oscillation. So we have alternating compression and rarefaction. The image at the top of the slide is not illustrating a transverse wave. Please make sure that you understand sound is longitudinal. But what we are looking at here is basically a graphical representation of the amount of pressure, or the density of those molecules within that space. So we have alternating high and low pressure. The compression phase would have a high value for pressure, and the rarefaction would have a low value for pressure. So once again, just illustrating those alternating phases about the equilibrium or resting position, which in this case would just be atmospheric pressure for sound. This particular image I think is really neat. So we see here that we have molecules that are being oscillated or vibrated, and you can see from the animation that the wave, or the energy itself, is being passed along from particle to particle so that it moves across the screen. But they have highlighted some atoms here with red colored dots to help you focus in on what is happening to the individual particles. So remember that it is the energy that moves, not the particles. The particles are oscillating, so pick one of these red dots and watch it just simply vibrate or bounce back and forth, but it's not actually traveling across the screen. It is only the energy that moves, but it's because these particles are colliding with other particles, and that is passing the energy along, but the waves themselves are staying in the same general area. So when we say that we have vibrating molecules, this is what we mean, but the energy is being passed along the space, or the environment, in this case through the air. Again, we can see that we have alternating compression and rarefaction phases. So when we're talking about creating sound, you need to understand that sound is created because of vibration of molecules. So when you strike a tuning fork or any other musical instrument, you are creating a vibration, which then in turn creates these alternating compression and rarefaction. As the object moves, it compresses the air molecules immediately next to it, and so as a result of that, we will get this alternating phase of dense, high density and low density air molecules. So this repetitive oscillating motion, again, is called simple harmonic motion, where it goes through that cycle repeatedly over and over and over again. When we have vibrations, those vibrations are going to be passed to the next molecule, or when it bumps into another molecule, it will pass that energy on. So in order for us to hear something, these vibrations ultimately need to make their way onto some air molecules. Then the air molecules will pass that energy across the room until it hits our ear. We then have an eardrum inside of our ear that is going to be pushed because of the air that comes up against it. And so that is how we hear. It's the pressure of the air pushing against our eardrum that creates the frequency that then triggers the nerve that then sends the signal to our brain. There are ranges of frequencies for humans. The average audible range is going to be from 20 to 20,000 hertz. So most humans can hear on the low end as low of a frequency as 20 hertz and as high of a frequency as 20,000. Now, this is an average. Can every individual hear this entire range? No. There are several different reasons for that. Some could be developmental abnormalities. Maybe there was some sort of trauma or injury. We do know that over time, it is common for us to not be able to hear as well, specifically on the high end of the frequency spectrum. And so this is because inside of our ear, we have these little sensors. They're little hairs that get swayed back and forth as that air pressure comes in. And eventually, I mean, if you were to just imagine something being pushed forward and back, eventually it's going to break off, or it's going to fatigue and fall off or break. So as we get older, just the repeated exposure to that pressure is going to cause some of those little hair follicles or those hair cells to be damaged. And so that means that whatever frequencies they were able to detect can no longer be detected, because once they are damaged, they don't grow back. So with age, yes, we are going to lose some of our hearing range, but just kind of in general, there is an expected or normal range. Anything less than that, we refer to as infrasonic. It's just too small or too low of a frequency for us to recognize with the human ear. And then anything greater than that, we would identify as being ultrasonic. And that just means it's a higher frequency than what our ears can detect. Now, this is the average audible range for humans. Different animals are going to have a different set of audible frequencies. Here it says how old are your ears. If you're interested, you can go to YouTube and just type this in if you want, or you could type in hearing test. And there are so many videos where they will play a variety of sounds for you to kind of give yourself a little hearing test unofficially. If you choose to do this, I do recommend that you use headphones in order to get the best quote-unquote response or results to your ability to hear. But this one in particular has a really good visual that goes with the video where they are showing you the different frequencies. So if you choose to view this video, I would like for you to look at the illustration that they give you of the different waves as the frequency changes, so that you can see how the wave itself is shaped differently, primarily seeing how those waves are closer together with the higher frequency. Some other information about sound that you need to know when we are talking about the frequency of the sound wave. So just to review, frequency is how often that wave occurs per second of time. So as the frequency increases, as the number of waves, that pattern increases, then our ears are going to receive that signal, and the brain is going to perceive a high or a low pitch based on the frequency. So for sound waves, the frequency determines the pitch that we hear. So a high pitch for a high frequency value, a low pitch for a low frequency value. Okay? Amplitude is going to represent the intensity of a wave. So if you recall, the amplitude is the maximum displacement from equilibrium. So the more our particles oscillate, the greater we move them from that equilibrium position, the greater the amplitude. So it does not change the wavelength or the frequency, so the sound is the same. The only difference that the amplitude makes on what we hear is the intensity. So when we are dealing with sound, intensity would basically be the volume. Really loud sounds have a very high or large amplitudes. It's a very intense wave, lots of energy coming to your ear, and so we would call that loud. We could have the same sound but at a very soft or low intensity, and so this just means that it's a lower amplitude. Okay, so amplitude controls or is responsible for determining the intensity of sound, and when we're dealing with sound, we typically just refer to that as volume. And then I just have a couple of fun facts here. Ultrasonic waves, like sonograms, are used to produce images based on the amount of time that it takes for that sound wave to be reflected back. This is very much like echolocation that several different animals use in order to navigate or hunt for prey. They send out sound waves and wait for that reflected sound to then determine how far away they are from an object, or in this particular image, from their prey. Now, the speed of sound, is affected by the medium in which the sound is traveling. So if we have sound traveling through air compared to sound traveling through water, or maybe we create a sound wave and press it up against some sort of solid surface like the wooden top to your desk or the metal leg of your desk, all of those different materials are going to cause that sound to travel through that material at different speeds. So you have an image here of 3 different states of matter. So just kind of in general, you should have an understanding that our solids have the molecules very tightly packed in together, which means that those molecules are going to bump into the next molecule really quickly, because they are already so close. And remember, the particles oscillate, but it's the energy that's passed on. So when the first atom bumps into the second atom, it passes that energy. When it bumps into the third, it is passed once again. So every time we are trying to understand how fast or slow, or how the material is going to affect the speed of the sound wave, we just need to remember that we are dealing with mechanical waves right now. So we are going to try to analyze the speed at which, or how the molecular arrangement is going to affect how quickly that signal is going to be passed through contact of those atoms, okay? Now, it also says that temperature affects the speed of sound. So when we are dealing with temperature, I need you to know that higher temperatures are actually going to increase the speed of the sound. So what that means, faster, increase the speed of sound. So what that means is the higher the temperature, the more energy those molecules have. So whether it is a solid, a liquid, or a gas, as we increase the temperature, we have basically fed more energy to those individual molecules. So although, yes, the spacing is still going to affect the speed at which it travels in general, if we are saying within a solid, we have a solid at, 32 degrees Fahrenheit, and then we increase that same solid and change the temperature to 50 degrees Fahrenheit. Well, in comparison, at 50 degrees Fahrenheit, my molecules have more energy. They are going to be moving faster. It's still in a state of a solid, so that molecular arrangement hasn't really changed, but because it's moving with more energy, it's moving faster, it's going to experience those collisions much more rapidly, and so it's going to then transfer that energy on to the next molecule sooner than it would at the lower temperature of 32. And so that concept can be applied to all the different states of matter. So higher temperature is going to cause a greater speed of our sound, okay? Okay, so then when we are not provided with a speed, so let's say that you're working a math question and it's telling you that we have sound that travels across the classroom, and the sound travels at a speed of 332 meters per second. Well, that is the speed at which the sound is traveling through that particular material. If you are not provided a speed in the question, then I would like for you to use 342 meters per second as the default speed whenever we are dealing with the speed of sound through air. Now, the Doppler effect is a phenomenon where we have a sound that is emitted, but the way that we hear the sound, or whoever is listening, the way that the observer hears the sound is actually not the true sound that is being created. So for example, here is what an idling motorcycle sounds like. So we're going to start up the motorcycle, but then listen to the idling sound. So So the motorcycle itself has this low rumbling sound. But if you've ever heard a motorcycle as it is driving up towards you and then it speeds away, yes, I know the volume is going to increase as it gets closer. That's not what we are analyzing here. But if we think about the pitch of that sound as the motorcycle approaches and compare that to the pitch that we hear as the motorcycle drives away, you can see that that pitch changes. It's a high-pitched sound as it comes towards you, and then it's a lower sound as it leaves. So the sound that the motorcycle creates did not change. If I knew the frequency of the motorcycle engine, that value is the same the entire time. But what we perceive that sound to be can change because the motorcycle is moving. So this is a phenomenon known as the Doppler effect. So anytime there is relative motion, so either whatever is creating the sound or whatever is hearing the sound, one or both of those objects needs to be in motion in order for us to see the Doppler effect. So it is a perceived difference in frequency in comparison to the actual frequency of the sound wave. So if my object is moving towards the observer, whoever is listening to the sound, you can see from the image here, my ambulance is the object creating the sound. If it is moving towards the observer, then because of the object's motion, those sound waves up at the front end up getting stacked up on each other. If you are the person, if you're the person in front of the object, when these sound waves hit your ear, the frequency of that pressure on your eardrum is going to be a higher frequency than what the object is actually emitting. So you are going to perceive that sound to be a higher pitched sound than the actual noise coming from the object. If you are the person standing behind the ambulance in this case, then as those sound waves are being emitted, because the ambulance is driving away from you, that is causing a larger gap in between the sound waves. So when these waves hit your ear, the frequency at which the pressure pushes up against your eardrum is now a lower frequency. Those waves are spread out, so your ear is going to receive a signal where that pressure comes in at a slower rate, or not, I should not say a slower rate, at a lower frequency. So that is going to change the pitch that your brain interprets the sound to be. Okay?
The Doppler effect.
So
in Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
In Sheldon's words,
it's the apparent change in the
frequency. The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency.
So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch.
The sound waves spread out, and so you hear them at a lower frequency, a lower pitch.
Okay, so if I am asking you to calculate the perceived frequency of the sound, this is the formula that we would use. So our formula says that F for frequency, so this right here is going to be the perceived frequency. So this is what the observer hears, okay? This Fs is going to represent the actual frequency, so the true frequency of the sound wave. So if I know that the motorcycle emits a sound with a frequency of 127 hertz, then that's where my 127 goes. The VO stands for the velocity of the observer, and the VS stands for the velocity of the source. So how fast is the person that is listening to the sound moving, and how fast is the object that is creating the sound moving? Those are the two different velocities that we have here. Now, the other velocity that we see here in this equation is actually the same velocity. So note, neither of them have a subscript, and that is going to represent the speed of sound, the actual speed of sound through air. Okay? So this is where I said if they tell you that the sound is traveling through the air at a speed of 332 meters per second, we would put 332 in both the numerator and the denominator. If they do not tell me what that speed is, then we will just use the average speed of sound through air of 342. So let's work through a practice problem. Miss Gonzalez is rushing to the hospital at a speed of 30 meters per second. A police officer sees her speeding and turns on his siren. His frequency, or the frequency of the siren, is 800 hertz. If the officer chases Miss Gonzalez with a speed of 35 meters per second, what frequency does Miss Gonzalez hear as the officer approaches? So we have Miss Gonzalez, and she has a speed of 30 meters per second. The police officer is turning on the siren, and so the actual frequency of the siren is 800 hertz. The officer is chasing Miss Gonzalez, which means that she is driving away from the police officer, and the officer is chasing Miss Gonzalez with a speed of 35 meters per second, so that is his velocity. What frequency does Miss Gonzalez hear? So they are asking me to solve for the perceived frequency. The sound is coming from the police officer, so his speed is the velocity of sound, and Miss Gonzalez is hearing the sound, so she is the observer. Fs is 800. Now, they did not give me the speed of sound. I don't know how fast the sound wave is physically traveling through the air. So for this question, I will just use our average speed of 342. And the equation says plus the velocity of the observer minus the velocity of the sound. So let's go back to our notes here. And it says that the velocity should be positive if moving towards the other object and negative if moving away. So let's talk about what that means. It says in the problem that the police officer is pursuing Miss Gonzalez. So that means that my police officer is driving towards Miss Gonzalez, so his velocity is going to be a positive value. So when I substitute in the velocity of the source, my formula says to subtract a positive 35. Miss Gonzalez is driving so that she is moving away from the police officer. So that means that her velocity is going to be a negative value. So when I substitute in the velocity of the observer, it says in the numerator to add these two values, but I'm going to add a negative 30 for her velocity. Again, we are inputting those individual velocities. Velocity is a vector. So if the person or thing that you are inputting the value for, so when I'm inputting the velocity of the observer, then I need to ask myself, is the person listening moving towards the other object or away? And so I will individually make that velocity positive if it's towards, negative if it's away, and then I ask myself the same question for my source. So now in my calculator, I'm going to say my numerator is 342 plus a negative 30, and my denominator is 342 minus a positive 35. So when we put this in our calculator, we get something that rounds to 813 hertz. So this means that Miss Gonzalez is going to perceive the frequency to be 813 hertz, although the actual frequency of the siren is 800 hertz. Okay, so because of the relative motion between the two objects, what she hears is different than the actual sound. It changes the pitch. Frequency changes the pitch. All right. The last thing that we need to discuss is something called intensity. And so here this is defined as the rate at which energy flows through a unit area perpendicular to the direction of wave motion. Remember when we looked at the image of the water and we had the rock or pebble or whatever it was that was dropped into the water and it made circular waves. And at that time I said, remember, we live in a three-dimensional world, so the wave is going to be sent out in all different directions. So the idea is the same here. When we speak, that sound wave actually is emitted in all different directions, which is why we have this circular effect around my moving ambulance here. So this first illustration is showing us that we have a sound source, and the sound is being spread in all directions, so it basically covers a spherical area. So the intensity is going to be the ratio of how powerful my sound is divided by the area of the sphere that it is traveling in. And so we can see from the bottom illustration that the farther away we get from the sound source, the greater the area that has to be covered. And so as a result of that, the power is being spread out, right? We're dividing it up so that each little individual square area gets less of the sound. So my intensity is going to decrease as we move farther away from the sound source. Now, 4 pi r squared is the formula for the area of a sphere. So we are seeing that our formula is I for intensity equals P over 4 pi r squared. It just means that my intensity is the ratio where the farther that I get from my sound source, the weaker the intensity, okay? Because that sound wave is being spread out so that it is basically being divided up so that all of the different space can hear that sound. The farther away you get, the lower the intensity. So here it just simply says that intensity and frequency both determine the sounds which we are able to hear. So if we were to all line up in a straight line and we put somebody at the front of the line and they speak, the person closest to the sound source is going to hear that sound loud and clear. The intensity is going to be great. There's going to be a nice strong amplitude so that the volume is loud and we can hear clearly. The farther away we get from our sound source, then the weaker the intensity, the more difficult it's going to be to hear that particular person speaking, okay? The frequency, obviously we've talked about the audible range, so the frequency of